Okay, example 2, we're going to find the flux through the elliptic paraboloid. Now the elliptic paraboloid does have to be completely closed, so the surface is going to be defined by z equals x squared plus y squared, and it is bounded by the top z equals 1, which means that it is closed in this case. So in order for us to do this, we need to well, let's go ahead and sketch it real quick. We don't need to do that, but let's go ahead and sketch it just so we have somewhat of a visual what we're looking at, because we didn't do an elliptic paraboloid on the first page, I don't think. So we've got our elliptic paraboloid. That looks like z equals x squared plus y squared, and it's going to stop here at z equals 1. So what we want is we want outward orientation. Okay, outward does not necessarily mean upward. Have outward orientation. That means that your flux is coming out in this direction, parallel to the surface. And then it also has to be coming out from the other direction. Now, here's the thing. We are going to find the flux through the surface, but we also have to make sure that we see what's going on up here as well. It's got to be a closed surface. So let's go ahead and find this by using let's find the surface integral first. So let's go ahead and let's do the top surface first. I think that'll probably be the easier one to do. So the first surface, we'll call it surface 1. This is the top. That's just that flat disk on the top. Now remember, it's the whole surface, so we do need to include the entire thing. So basically we are looking at this right here as an entire thing. It's not just the outside ring. So we got to do that. So let's go ahead and parameterize that. Okay, we can do this in polar very easily. So x here is going to be r cosine theta. Y is going to be r sine theta. And z is just going to be 1 because it's at a height of z equals 1. So that's our r without specifically writing the r. We're going to have to do r sub r. And the partials with respect to r are going to be cosine theta, sine theta, 0. The partials of this thing with respect to theta are going to be negative r sine theta, r cosine theta, 0. No zeros in the last components of k make things really nice here. So let's see. R sub r cross r sub theta. If we eliminate the I row and column, basically we're going to get 0 minus 0, so that's 0. If you eliminate the j row and column, you're still going to get 0 minus 0, so that's really nice. Eliminating the k row and column, we're going to have r cosine squared plus r sine squared, which of course we should know by now is just going to work out to be r. Okay, and we're talking about this top disk, so we want r to be positive, so that's good. Okay, that's a good thing. Now when we go to parameterize the force, and this is not something that we would normally do, we parameterize the force because we know we're going to have to dot these two things. I don't really care what this one is. I don't really care what this one is because they're going to get dotted with 0. I do, however, care what the last one is, so I do have to parameterize z squared, but z itself is 1, so z squared is 1. So we're going to go ahead and we're going to set up our double integral. And remember, it was the dot product, so the 0 times whatever is 0, 0 times whatever is 0, and then all we have left is r. Okay, and we've already parameterized it in terms of this, so we don't need an extra r for our dr d theta. Okay, we do need to figure out our bounds. R is going to go from 0 to 1, because if z is 1, your radius is 1. And theta, of course, goes from 0 to 2 pi. So our top disk here is going to have integral from 0 to 2 pi of d theta times the integral from 0 to 1 of r dr. So we know the first one gives us 2 pi, and then we get 1/2 r squared from 0 to 1. But that's just going to be a half minus 0, so it's a half. So ultimately, what we get is 2 pi times 1/2, or pi. Okay, so that's the flux going through the disk. Now we need to do the flux, surface number 2, through the paraboloid portion of this thing. So we'll call this the, I don't know, just call it the paraboloid portion. I'm not going to call it anything. So we're going to parameterize this one. I'm going to choose to parameterize. You could parameterize this one right away in terms of cylindrical or polar or however you decide to do it. I'm going to just parameterize this one using the trivial parameterization. So I'll let x equal x, y equal y, and z is defined as x squared plus y squared. To me, I like doing it this way for a paraboloid because it's easier for me to take the partials and then I can re-parameterize it later if necessary. So that's not going to be that bad of a thing. So let's do r sub x, which will be 1, 0, 2x, r sub y, which will be 0, 1, 2y. We're going to have to do the cross. So we'll have r sub x cross r sub y. Okay, so eliminating the I row and column, we're going to get 0 minus 2x. So that's minus 2x. Eliminating the j row and column, we'll get 2y minus 0, but we changed the sign. And then eliminating the k row and column, we get 1 minus 0, which is 1. Okay, this is bad. We don't want that because that actually indicates that we have an upward flux, and we want this to be outward. We want it coming out of the paraboloid. So we actually needed that to be negative, but easy fix. We're just going to change this to ry cross rx. Change all the signs. So now we will have a downward flux. Perfect, outward. Okay, so we do have to parameterize. So let's go ahead and parameterize. Now this one we actually do have to parameterize because I have a component of my normal vector in each piece. So f here, parameterized, is going to be, let's see, y is just y, x is just x, and z squared is x squared plus y squared squared. There we go. Okay, so now let's parameterize. So now we have to dot these two things. So if we dot them, let's see, what are we going to get here? We're going to get 2xy plus 2yx or 2xy, and then minus x squared plus y squared squared. Excuse me, that's our dot product. So we would have to take the double integral over that dA over our domain. Alright, so now let's go ahead. I'm actually going to simplify this real quick because the 2xy plus 2xy is obviously 4xy minus x squared plus y squared squared dA. Alright, now I'm definitely going to want to do this because I don't want to, I mean, you definitely could FOIL x squared plus y squared out, and then you could do this with respect to x and y. It would not be horrible, but I think it's going to be easier to go ahead and put it in terms of polar because of the x squared plus y squared. So let's change this into terms of polar. Scroll this up just a little bit. Okay, we're going to do our double integral. In polar, x is r cosine theta, y is r sine theta, so we're going to have 4 r cosine theta, r sine theta. X squared plus y squared is r squared, so that'll be r squared squared, and then we'll have dr d theta. And let's see, in this case, r could go out to 1, so 0 to 1, and theta goes from 0 to 2 pi. Okay, so let's go ahead and work this out. And you might be asking yourself, well, wait a minute, didn't you forget the extra r? Yes, I did. So let's go ahead and put that in here, r, because I did forget. We did not We did not initially parameterize this in terms of polar, so when I changed it to polar later, I have to put in the extra factor of r. Okay, so let's go ahead and distribute everything and see what we get here. So we are going to get, let's see, the first part is 4r squared times another r, so it's 4r cubed cosine theta sine theta minus, let's see, r to the fourth times another r is r to the fifth, integral 0 to 2 pi, integral 0 to 1, dr d theta. And that looks right. Okay, unfortunately, there is no way to separate these completely, so we're just going to have to go piece by piece. So let's do the r part first. Scroll down, give myself a little more room here. Antiderivative of the first part with respect to r is going to be r to the fourth cosine theta sine theta minus 1/6 r to the sixth, and we're going to evaluate that from 0 to 1. Don't forget your d theta and your 0 to 2 pi integral. So let's see, if I plug in 1, we're just going to get cosine theta sine theta minus a sixth, cosine theta sine theta minus 1/6. Plugging in 0, because sine of 0, because it's 0, it makes everything go away. Okay. Now let's take the antiderivative with respect to theta. Technically, we should split these. However, when we split these, you're going to have integral of 0 to 2 pi of cosine of theta sine of theta. When you do a u substitution, because the integral goes from 0 to 2 pi, what doesn't matter if you let sine or cosine be your u value, it's going to end up with giving you an integral from the same value to the same value. So we know that that part right there is going to go to 0. Okay, you can work that out if you need to see it, but that part is going to go to 0. I still have to take the antiderivative, however, of the negative 1/6, and that's just going to be negative 1/6 of theta, and I have to evaluate that from 0 to 2 pi. So plugging in 2 pi, we're going to get negative 2 pi over 6, which is negative pi thirds, and plugging in 0, we get 0. So I get negative pi thirds. Now the total flux was the sum of these two things. I have pi going from the disk, and then negative pi thirds coming from the paraboloid part. So ultimately what I get there is 2 pi thirds. Again, not horrible to do it that way, but now let's go ahead and verify this using the divergence theorem, and we will see just how much shorter and how much easier this really is. So the first step is to actually find the divergence. Let's find the divergence of f. You do have to scroll back up in this case. F was y x z squared. So x was y x z squared. And remember, it's the partial with respect to x, partial with respect to y, partial with respect to z, dotted with our force. This is going to make things really nice, because the partial of the first component with respect to x is 0. Partial of the second component with respect to y is 0. Partial of the third component with respect to z is the only thing that gives us anything, that is 2z. So there is our divergence. So in order to do this, we're going to set up our triple integral of 2z. And I don't see why we shouldn't go ahead and go in terms of cylindrical here. So that would be dz r dr d theta. Now the biggest thing is how am I going to do z here? Well, we'll come back to z in just a second. We know theta, because it's a complete circle here, is going to go from 0 to 2 pi. Okay, the r part we know goes from 0 to 1. It's the z. So let's go back up to the top real quick and take a look. Z was x squared plus y squared. So I know that z is the same thing as r squared. That's the bottom. Okay, that's this bottom piece right here. That's the elliptic paraboloid part. So z is going to go from r squared up to 1 there where it stops. So that's my bounds for z. So let's go ahead and plug that in. Z is going to go from r squared to 1. Okay, and then it looks like we can go ahead and start taking the antiderivatives here. So the antiderivative here with respect to z, is going to be z squared. And we'll evaluate that from r squared to 1. Okay, we still got this r, dr, d theta. Still got our bounds for those two pieces. So let's see, plugging in 1 is going to give me 1. Plugging in r squared is going to give us r squared squared, which is r to the 4th. So I get 1 minus r to the 4th. Still have this r, dr, d theta, 0 to 1, 0 to 2 pi. Okay, these can now be separated. I can distribute the r, which I'm going to do. It's going to give us r minus r to the 5th. And that'll be the dr part. Excuse me. And then I know that I'm going to have an integral from 0 to 2 pi of d theta, which of course is the easy part. So let's see what we get. We know that's going to be 2 pi. When I take the antiderivative here, we're going to get 1/2 r squared minus 1/6 r to the 6th from 0 to 1. So we're going to get 2 pi. Plugging in 1, we get 1/2 minus 1/6, and then plugging in 0 gives you nothing. 1/2 is 3/6, so 3/6 minus 1/6 is 2/6. Did I do that right? 3/6? Yeah, 3/6 minus 1/6 is 2/6 times 2 pi. Let's just write this out. 2 pi times 2/6, but 2/6 is 1/3. So we get 2 pi thirds. Same exact answer. Much, much shorter to do. All right, 3 more examples.